Assalamu alaikum, hello everyone. So in the previous session we started with linear transformations. So I'll just give a brief overview of linear transformations again. So we started with linear transformations. So in that what we said in graphically we saw that if there is a vector and if we apply some transformation on the whole space, so it will take a vector somewhere else. Let's suppose in that we showed a video to you. So let's again play that video. Suppose this is a vector that is our input vector, and if we want to warp out the space and somehow this got into convert into that output vector that we have right now. So by the transformation I mean that whole space got sort of shifted. So what is the way the whole space will get shifted? You will see that in the animation. So let's consider all these are vectors together. So this is all the vectors that are available in our 2D plane. So if we apply any transformation, so what will happen that it will squeeze or it will extend this whole space, and you see that every vector sort of shifted here and there. Okay, so if you consider all of these vectors as just points in 2D space, so like this, if these are the points that we have, so if you now consider the linear transformation, that means you are rotating these lines but keeping the origin intact, keeping the origin fixed, and then moving the lines in such a way so that they become parallel and evenly spaced. So let's suppose this is the transformation that we want to do. So this is what will happen. So these points will become, again these points will move on to somewhere else, and that's what I mean by linear transformation. So again showing you some transformations. So here it is. There are a lot of transformations that we can do. Okay. Again taking the example, what we did is that, for example, if we have a vector, let's suppose 2, 3, this is our vector. Okay, so we can represent this vector as 2I cap plus 3j cap. Okay, that is we can write this in component wise. This is this x component, I axis or x axis, then we have y axis. So if we apply any transformation, so what I said is that, so in order to see this transformation, you just need to see where this I hat and j hat line. Let's suppose this was vector x. So we said if there is a vector x, some random vector x, so it can be represented by a some vector v1, that is the basis vector, plus b v2. Sorry. So what I said is, suppose we have a vector x which is equal to 2, 3, and we can write it as 2I cap and 3j cap. So if we apply any transformation onto this vector, so we can represent this vector x, let's suppose like this, let's suppose it's a generic vector. So this can be represented as a v1 plus b v2. Let's suppose this x was 2, 3, so a here is equal to 2 and b is equal to 3. So v1 is basically the I vector 1, 0, and then we have v2 that's equal to 0, 1, if you see in this setting. So I wrote a generic vector like this. So this is a generic vector. So what I told you is that if we transform this, so there is a vector x, so we applied some transformation. So if I applied some transformation, so what will happen to that is that we'll get some transformed vector. But in order to get the transformed vector, our job is to see the only two things, that is where this v1 went and where this v2 went. We only have to keep track of this. So we can write t of x, so transformation of this x vector, it's equal to keep the coefficients as they are, a and then t of v1 plus b and t of v2. This is what actually is meaning of the linear transformation. So if I again show you the animation, so basically let's suppose we have this vector v that's minus 1, 2. So it can be written as like this, minus 1 I hat plus 2 j hat. So if you now have a transformation, let's suppose we'll just play a transformation like this. So we transform the whole space. The only thing that you have to keep track of this I hat and j hat. If you if you again see, sorry, if you again see, this is our I cap and this is our j cap, and now you want to see where they transform. Just keep an eye over these vectors. So this is our transformed I, so this is our transformed I vector, and this is our transformed j, and this is our transformed v vector. So what I'm telling you is that this transformed v, it can be computed by this negative I transformed I cap plus 2 j cap that is transformed as this j cap that we got transformed. So how to compute this basically is like this: transformed of v is equal to minus 1 transformed of I plus transformed of j cap. So in order to compute that, we wrote minus 1 1 2 plus, and these are the vector values, the transformed vector values, and we can compute that. If you see, this is the computation that is done on the screen. This is how we can compute any vector. That's what I meant by the transformation. Okay, so there are some famous transformations. For example, there is a transformation which I call as rotation. So let's go to that rotation. So this is, let's suppose we have this vector j cap and we have this vector I cap. So let's suppose I want to rotate this by 90 degree. I just want to flip this I cap towards the negative so that I'll rotate the whole space with 90 degree. Let's suppose I want to do a rotation like this, 90-degree rotation counterclockwise. So actually what happened, this I cap now, this j cap moved over here and this I cap came at the j cap. So how can we represent this in an actual matrix? We just need to keep track of these vectors, this basis vectors, this I cap and this j cap. So what we can write in the I cap is that 0 1, because this is where the I cap landed. I cap landed 0 1. So we'll make this as one column of the matrix. So this is made as one column of the matrix. Then we have this j cap. So j cap's value is minus 1 0. So we'll make this is other column. So this matrix here represents actually the rotation. So if you ask me, like if you are seeing a video on the YouTube, if you are playing any game, so you might have seen there every scene is moving and something is rotating, something is moving here and there. Everything that is done there is by using these rotation matrices. So these rotation matrices are really important. That's the importance of these things, because everything that's happening in the graphical interface, whether you are making a game in which the scenes are changing, so everything that happens there is basically happening by the means of linear algebra. So now we have this matrix, we'll call it a rotation matrix, let's suppose. So this is our rotation matrix. So if you want to rotate any vector by 90 degree counterclockwise, so you'll just apply this matrix onto that. Okay. So this is again, this is another rotation. We call it a shear rotation. So we have, so this is the rotation that I'm talking about. So here, so if we have a space, so if it got rotated like this is called a shear. So in shear again, we'll have to just keep track of these where I cap and j cap landed. So the I cap remained as it is 1 0. So we'll just write it 1 0 as it is. And but this j cap, if you see, it landed at 1 1. So we'll write 1 1 here. So this basically is actually a shear transformation. So this is called a shear, if you see it. So if you take any vector, for example, like this, and apply shear onto this, so this landed over here. So now we can capture these things in a matrix. So as I told you that we can capture every transformation with this. So in the transformation, let's suppose we are talking in 2D case. So in 2D case, what will happen is we'll just keep a track of where I hat went and where j hat went. That is these two bases. So let's suppose we have this went towards, let's suppose A, B, and this went towards C and D. If we want to compute the what this transformation did to any other vector, let's suppose that vector was x1 and x2. Okay, as you know that initially this vector would have been represented by, let's suppose this vector here is x, so it would have been represented as x is equal a, or maybe x1 I hat plus x2 j hat. So this is the actual representation before transformation. Now we applied this transformation. So now we applied this transformation. So what will happen to this transformed of x? So how will this vector transform? So this will get transformed like this. So x1 will remain as it is. So this I hat will become transformed of I hat plus x2 will remain as it is. So because these are coefficients, so they won't change. So this will be j cap. Now you know that these are transformed vectors. So I can write x1 and then ti cap is basically this vector ab, and then x2, this tj cap basically is this cd. So I'll write this cd over here. So if I just expand it, I can write x1a plus x2c and x1b plus x2d. So this is the final vector. This is the vector that we got out of this. Let's suppose this vector is, let's suppose some vector w1 and w2. This is the transform vector. So this w2's and w1 and w2's value is this much. So this is the meaning of linear transformation. I also showed you a different linear transformation. We saw what is 90 degree counterclockwise, and we saw also a linear transformation known as shear. So I can move ahead with this. So I told you that again to reiterate. So linear transformation in that when you transform a space, the origin should be fixed. Origin should be fixed. That's the first property. And the second thing is these lines, whatever these lines we had, they should be evenly spaced. They should be evenly spaced and parallel. So they should remain parallel and should be evenly spaced. That's what we count as linear transformation. Then we saw the mathematical reasoning, what transformation basically is. So now from this you got to know the matrix multiplication. Why do we do the matrix multiplication in the way we do it? Okay, so this is the whole agenda behind that. So we are having some vector, transform vector I cap, transform vector j cap. Then if we have a random vector x1, x2, and we want to see what this basically is a transformation matrix. I can call it transformation matrix. Okay, now I'll if I want to see where any other vector landed, so I'll just take that vector and I'll apply the transformation, and that's where this multiplication concept comes in. So now we'll move into the multiplication of matrices. So is the revision of linear transformation clear? Then I can move ahead. If transformations is really clear, then only can I move ahead. Is it clear? Nice. Again, should just write that if we have any generic transformation a b c d, that is the I vector landed here and the j cap landed here. This is in the 2D space. So if we have any generic vector, let's suppose x1 and x2. So after transformation, what will happen is, so this basically will get multiplied to this vector. So x1 will get multiplied to ab plus the x2 will get multiplied to cd. Okay, this is the transformation vector where this vector will land, but geometrically speaking. Now I need to sort of see, let's suppose we saw these two rotations, we saw two transformations. Transformation one is, let's suppose that 90-degree counterclockwise transformation, sorry, counterclockwise transformation. Then we saw t2 other transformation, that was shear transformation. Okay, let's suppose what will I do is I'll first apply this t1 and then I'll apply this t2 and I'll see what will happen to the space. So if I will do that, so I want to see what will happen to the space and I want to capture that sort of transformation within our framework. So if I just show you in the animation, maybe should be here, yes. So now let's suppose we have this rotation first, then we'll apply shear. So initially the space is like this. If we see the space is like this, so we have this I cap and we have this j cap. This is the original space that we have, original two-dimensional plane. So now we'll apply the rotation first. So what we'll do, we'll apply this 90-degree counterclockwise rotation. Okay, then we'll apply the shear. So you saw we applied one transformation first, followed by the other transformation. So if you take any vector now, if you take any random vector and you want to see what happened because of that transformation, and you'll have to capture it. So we call basically this, if we apply this transition, if we apply one rotation then followed by other rotation, we call it composition. Composition. So in composition, what we did is we applied rotation first and followed by shear. And we have even named them. We have the matrix for the rotation, we have the matrix for shear. But here we compose two rotations. You can compose multiple transformations as well. This is a linear transformation, this is another linear transformation. So we on the space we applied rotation first and we applied the shear second. So these are called composition of rotation and shear. We call them as composition of linear combinations, if you call them composition of linear combinations of, sorry, of linear transformations. Okay, so now if you take any vector, in the space, so what will happen to that vector? We want to see that. So the only thing that we have to do is we have to record where this I and j will land basically. Okay, so that's our goal. So we want to see where will this I hat and where will this j hat land. Okay, let's move and see what will happen. So I'll just show that again on the animation. Let's suppose we have this. We have to keep the record of where the I hat and j hat landed. So this is after the rotation and the shear. Now we'll capture where this I hat and j hat landed. So this I hat landed at 1 1 and the j hat landed at, so this is the, we can keep it in the column and then we can see where this j hat landed. So j hat basically landed at minus 1 and 0. So this is what minus 1, we'll keep this as second column. So this matrix now represents this 1 1 minus 1 and 0. This represents the composition of a rotation and the shear. So initially we saw how to make a rotation matrix. So we saw in the rotation where will this I hat and j hat land. So in the second scenario, when we apply the shear, so in the shear what we did is we also kept the same thing where this I hat went and where the j hat went. We made a separate matrix out of that. But if we apply the composition of these things, composition of rotation and shear, so if we want to capture that, so what we did is we'll just transform by using the rotation first, then transform by using the shear first, shear second. So what will happen there? So we'll see why this I hat went. This I hat went to 1 1, so we captured that in 1 1 over here. Then this j hat went to minus 1 0, so we captured that over here. So now in order to see where this matrix come from, so there is where will what will happen as we'll see where this matrix multiplication came from. So we applied the rotation first, so we got this column 1 1, then we applied the shear, we got this minus 1 0. This is what happened. The actual effect was basically this matrix. Let's suppose this is any random vector. Let's suppose this is a vector. So we want to see after applying this rotation and shear what will happen to the vector. As I said that in any linear transform you just have to keep track of these basis vectors, basically this I hat and j hat. We're speaking this in 2D. This can be extended in 3D as well, in ND as well, but ND we cannot imagine. But that's the reason I want to give you intuition based on 2D and 3D. And in the ND you have to extend that intuition. So now we'll apply the rotation first. This is where the vector landed after the rotation. Now we'll apply the shears. Now we applied the shear, so this is where a random vector landed basically. Let's suppose we have this vector xy. Okay, so this is the application of rotation. So we'll apply rotation basically onto this. Then after that we'll apply the shear. So we'll apply the rotation first on a random vector xy, and we'll see where will this land. And after the application of the rotation, then we'll apply the shear, and we'll see where the xy will land. Okay, so this is our rotation matrix, and this is our shear matrix. So if you want to see it, if you want to compute it by hand, so how can you do that? So let's compute these things by hand. So we have a vector, let's suppose a random vector x and y. So what will we do? We'll first apply rotation onto this. So we'll apply rotation onto this first. So we'll apply rotation. So what is the rotation matrix? So in the rotation what happened is x basically got to 0 1 and y basically went to minus 1 0. So this is the rotation. So after capturing this wherever this went, so we'll do one thing, we'll apply the shear 1 0 1 0. So this is what we'll do. So this is shear, and we know that, so we have already captured that, we know that it will take this xy where, so we have seen the matrix previously. So when we had these composition of these things, so we saw the matrix. So what was the matrix? Basically the matrix was 1 1, and the other column of matrix was minus 1 0. So this here represents basically, this represents the composition of rotation and shear. Okay, so what I did is actually when I showed you the animation, so in the animation I told you that my screen is not properly visible on the tab. What happened? Let me just figure it out what happened. Sometimes there are random technical glitches. Okay, is the screen perfectly visible now?
Yes, sir.
So initially did it got warped and was it smaller?
Fine.
Okay, right. So what I told you that, so we had this vector xy in here, so we applied rotation onto this. Okay, so it went somewhere. Then after this, to the whole of this we applied this shear. So but we saw that, how did we capture this? We captured that by a matrix here. So this matrix over here, if you see it, this matrix, so this basically tells me this is the composition of rotation and shear, if you see it. But as you saw that this rotation is a separate matrix and this shear is a separate matrix. Okay, so are you with me till this point? Are you with me till this? Do you sort of accept this, that this matrix over here, this matrix, so this matrix is composition of rotation and shear? Okay, that's the thing I want to establish first, because after this we'll connect the matrix multiplication with the linear transformations. So this I want you to ingrain this into your head. So that means that this shear and rotation, that is shear and rotation matrix, this must be equal to the composition matrix. Composition matrix, that is this matrix over here. So I think I have, so this matrix, rotation matrix should be, it should be something else. I think this is 1 1, sorry, this is 1 1. So here the shear matrix is 1 1, so we applied 1 0 1 1, and the rotation matrix is 0 1 and minus 1 0. Okay, so that we got this matrix, composition matrix, 1 minus 1 1 minus 1 and 1 and 0. Do you agree with this? Let's call this shear and rotation, let's call this C. So do you agree that these should be equal? Because what basically I did is, on this vector xy, I first applied the rotation and then applied the shear. So this is what I did basically. So on this xy, I basically took the composition of that matrix, whatever happened in that animation. So that's what is basically shown in here. So what I what I'll capture this is now that how this multiplication is basically done. So if I want to expand this and if I want to expand this, so how will the expansion work? So that I want to show you. Okay, so what will I do? So let's suppose, as you know, that we have some vector x and y. Let's suppose we have this x and y vector over here. I'll just put an equality over here and I'll write we have this x and y over here. And we have these vectors, so 0 1 minus 1 0. So we applied a rotation first, so what will happen? This x will get multiplied to whole of this column. So 0 1 will be multiplied to x, plus this y will get multiplied to this y multiplied to minus 1 and 0. If we sort of expand this, so this will be minus y and this will be x. So if you just expand this out, so this will be equal to this. So we did this part of the calculation. We did this part of the calculation, if you see. And now we're applying shear. We are applying this. So if you apply shear onto this, so we have a vector minus 1x. So actually what we had a vector xy. So after applying 90-degree rotation, so we had this minus y and x. So now we'll apply this shear matrix. The shear matrix basically is 1 0 1 1, if you see it over here. So this is our shear matrix, 1 0 1 1. This is the matrix. So now again you know that, just take this coefficient, multiply with the whole column, minus y 1 0 plus x 1 1. So this will be equal to, so if you see it, it will be minus y plus x, and then 0, this will be plus x over here. So this will be a transform vector. So if you again see it, if you again see the right hand side now, so right hand side, we had this matrix 1 1 minus 1 1 1 minus 1 0, and if we multiplied it by x and y, so that was our initial vector. So if you multiply this, so it will be x multiplied by 1 1 plus y multiplied by minus 1 0. So this will be also equal to minus y plus x and x. So both of these give the results true. That's how I was justifying this equation, that this is equal. Okay, now what I will do is, I'll first compute the shear and r, and I'll here you can see that what I did is, I first had a vector, let's suppose x, and I applied rotation onto that, and on the whole thing I applied shear. So what I want to do is, I basically want to compute the composition matrix first. I'll just apply this composition matrix C and then apply this X. So if you see this SR, in order to get the C out of it, now you have to perform the matrix multiplication. That is the intuition you saw is here. So why the matrix multiplication is done is in a certain way. So if I now take this SR matrix, so S basically was 1 0 1 1. This was the shear matrix, and the rotation was, if I'm right, this was 0 1 minus 1 0 0 1 1 minus 1 0. So what I can do again is, let's take this as a vector. So let's suppose this is a vector, and we want to see what will happen if we apply shear onto this. So we'll do one thing, we'll take this 0 and multiply with the whole column, 0 1 0, plus we'll take this 1, multiply with this. Okay, so this will be 1 multiplied by 1 1. Okay, so we are just taking this vector. So as if this does not exist till now. So we'll get so we'll get out of this, we'll get, so this will be 0, we'll get 1 1, because this will be multiplied with 0 and we'll get 1 1 this. So this will be the first column of the composition matrix. So now if we take the second column, okay, if we take the second column, again the similar way we'll multiply it. So minus 1 multiplied by 1 0, then minus 0 plus 0 multiplied by 1 1, so it will be minus 1 0. So minus 1 0 will be the other column because of this. So I just treated this, where will this land and where will this land, because the share. So this is where they landed. So I got on multiplication of SR, I got the C. So you saw how the multiplication is basically done without giving you that memorized way in which you will multiply the column then the row first. So do you understand how the multiplication is done? Zubair, have you understood? Now if you tell me what multiplication basically is, so I'll tell you matrix multiplication basically is the combination of linear transformation, some composition of linear transformation. Okay, so if I have to define what matrix multiplication is, what is matrix multiplication, I'll just say it is composition of linear transformations. And you know what linear transformation is, that we have discussed in detail. So now I want to show you the ways of matrix multiplication. You just saw some ways, so I show you the ways of matrix multiplication. Ways of matrix multiplication. These intuitions should be sort of concrete in your head, because whenever you are doing, these images should pop out into your head. If you see a vector, you must have that picture in your mind. Oh, actually this vector lies in some vector space. So if we do apply any vector if we apply any matrix that basically means we're applying a transformation onto that vector, and that vector will land at somewhere. It's very unfortunate that these topics are not introduced in this way in your +1 and +2, but they are really heavily they basically were made for this, made for so that we visualize. I told you that whenever you are doing this computer vision and all of the graphics and things on the computer, it's happening because of this matrix multiplication. If you remember, I once told you a case study. So what happened in, I think it was a case study in US. So there was a truck driver, he was driving, so some set of robbers, they came and they stopped the truck, and they dragged truck driver out of it, and they looted whole of the truck, whatever was there. So in order to solve the case, what happened, so they had to see the CCTV footage of the thieves. So what happened, they haven't, basically they have covered all of their face and all the things, so but they saw a tattoo on the arm. So by using the algebra, they could detect the edges of that tattoo. So when they detect the edge, they could reconstruct the tattoo from by using the algebra, linear algebra. So after that, they showed it to the company who made the tattoo and told them who is the person who basically got this tattooed on his body. So they gave the person's name, and this way they were able to sort of capture that thief. This is just one case study. There are a lot of case studies that where the linear algebra is used. So having this intuition set into your mind and knowing the geometric interpretation of all these things, now I want to delve into some mathematical the tricks, basically mathematical details, which will help you to sort of make this multiplication really easy. So the first way, as you saw, is that, so if we have a vector like this, if we have a matrix 1 2 4 1, so if we have another matrix 2 1 3 4, so now what you can do is you can first do the first, I will call it traditional way. Let's name them traditional way. So what's the traditional way? You might have seen that we'll take one row and then we'll take one column. Okay, that will be the entry. Let's suppose this matrix is C over here. This is A. Let's call this matrix B. Let's call this matrix C. So in it, if I want to find this entry, so I'll take the first row. If I want to find basically C11, so C11, how can I find C11? I'll take the first row of the A matrix and I'll take the first column of the B matrix. So I can write, traditional way is basically, so if I want to find any entry, let's suppose C, any entry, so I'll write row of A multiplied by basically dot product of column of column of B to get an entry. Let's suppose this entry is let's suppose 2 3. 2 3 is not there in entry. Let's suppose it is 1 2. So I'll take the first row of A and the second column of B and the second column of B. So in order to get this C12, so I'll take the first row and the second column of B. That's the generic intuition how this traditional way multiplication works. If I have to write Cij, So what I'll do is I'll take the ith row of A and dot product it with the jth column of B. Jth column of B. Okay, so how I'll do it? So ith row basically means if I have ith row, so there will be I1 element I1, then it'll be element I2, element I3. So AI1, AI2, AI3, and so on. So this will be a row. So column basically over here in the J. So it will be jth column will be, let's suppose this is jth column, this is ith. Let's suppose we have a jth column over here. So jth column will be, so 1j, 2j, 3j, and so on. So it will be bij. Okay, so I can write it like this. So I can write a I1 multiplied by this b I j plus, take the second entry a I2, and then this b 2j plus, and so on. So here I can write in the succinct way, I can just write summation of a I and j, then I write b, and you can see this I11, this 2 I can write it as k. So this k goes from 1 to n. So this is the entry Cij. Is it clear? So this is the succinct way if I want to get one entry in out of this. Is this clear where I got this from? Zubair, Rian, is it clear?
Yes, sir.
Rian, are you there? Okay.
Yes, sir.
So did you saw how I derived this? Basically, you might have seen a lot of notations in written mathematical books. So that looks scary sometimes. So this is basically how we derive this. First, having the intuition back in the mind, then we saw what is the first additional way. We just multiply a row by the column. Okay, then we get this formulation. And if this is the entry. So again, this is for example 1 2 3 4 1 2 3 4 5. So if I talk about this element, so here this element will be, let's suppose this matrix is A matrix. So over here I can call this CA35. So we call it a dimension. So this is of 4 cross 5 because it has 4 rows and 5 columns. So these are called dimensions of matrix. Dimensions of matrix. Now you also understand, because of this, because of the intuition that you have, you understand why is it required that if you want to multiply matrix A and B, so the number of columns basically in A should be equal to the number of rows in B. So the number of columns of the first matrix, that's A, should be equal to number of rows, because of the linear transform. If you trace it back, you will know. So if you want to multiply anything, so for example you are multiplying a vector, so here it should be n by k. So these things should sort of match, otherwise the matrix multiplication is not compatible. So this is the first traditional approach, how you were taught the matrix multiplication back in your high school, or +1 +2, like take this row and take this column, and then how we derived this. This is the first approach. Let's see the second approach. I call this, let's suppose, the column way. I'll just name them so that you remember them. Column way. What is the column way? So let's suppose we have this matrix 1 2 8 1. So this is our one matrix, let's suppose A. Then we have a matrix 2 4 -1 0. So this is our and the matrix. So as you know that, for example, let's suppose this matrix, this part does not exist. Let's suppose this part is not there. Now you know that how to multiply the matrix. So you will just take this and multiply it with the columns. But we know that this exists. So just for time being, you just keep this does not exist anywhere. So we'll just focus on this 2 4. So as you know that how we can write is that we would use to do in the linear transformations, we write this 2 then multiplied by 1 2, then plus this 4 multiplied by 8 1. Okay, so this basically is equal to 2 4 plus 32 4. So this is equal to 34 8. Okay, so I can make this as the first column. Whatever the C is, I'll make it the first column. Now I'll see that this does not exist, let's suppose. So if we had only this column, so what will happen again is I'll multiply -1 with whole of this. So it will be -1 -2. So 0 multiplied by 8 1, it will be 0. So I'll be left with -1 and 2. So this is the R matrix A, this is our matrix B, this is our C. So if you understood the concept of linear combinations, can I tell that the C matrix, basically the columns in C are linear combinations of columns of A. Can I say this? Because if you see this column, this was just made out of these two columns, and the linear combination was taken. The first column was multiplied by 2 and the second column was multiplied by 4. So basically this column is a combination of the columns of A, if you see it that this way. So I'll again reiterate. So what I told you, that in this matrix C, if you see, the columns of this matrix C are the linear combination of columns of A. So because how I got it? So I got it like this. So I took this 2 and multiplied with whole the column, then plus. I took this 4 multiplied with the whole column. That was the whole concept of linear combinations. So a linear combination was if you have a vector v1 and if you have a vector v2. So if you say, let's suppose a v1 plus a v2. So this basically was a linear combination of these two vectors. So here, do you agree that I can call that this columns in C are the linear combination of columns of matrix A? Can I say this? I want a verbal response.
Yes, sir.
Okay, so this is the second way, the column way. I just chose the columns and then I represent this way. This is the second way you can multiply the matrix. The first way was you can just take the dot product of the rows and columns. The second way is that you can just take the columns of a matrix A and you can take the linear combination. Let's now see the third way. Third way, I'll call it a row way. So again, taking the similar matrix, let's suppose we'll take 1 2 8 1. This is our first matrix, 1 2 8 1. So that our answers are consistent. 2 4 minus 1 0. 2 4 minus 1 and 0. So what I'll do is now I'll basically take the row of this matrix, row of this matrix. I'll take these are the rows of this matrix. If you see this matrix B, this is matrix A and this is matrix B. So what I'll do is I'll take the row of this matrix and multiply it with these numbers. Okay, so if you see for example how we perform the dot product, so what I'll do is I'll take the rows. So I'll just take the first row. Let's suppose this row is there. So I'll do one thing. So I'll do 2 minus 1 is like this. Okay, let's suppose we multiplied this whole vector, let's suppose by this one. Okay, we'll multiply whole of this with 1. So basically what I was telling you the result upfront so that you understand where am I going. So we'll get some matrix C over here. So what I can tell about this C is the rows of C are linear combinations of rows of B. This is what I'll get. So as we saw in the first case, the columns of the C were the linear combination of columns of A. In the similar fashion, when I'll do the multiplication with row, so what I'll do is I'll just consider the rows of this matrix A, this matrix B, and take the linear combination out of this. Okay. So in order to get the first row, what I'll do is I'll take the whole matrix and see if I only had one row. Okay. So what I'll do here is, so again by if you see this 1 and this you see this 2 4, so I'll take this 2 1, so this basically is a row. Okay, then I have to get some coefficient over here plus some coefficient over here and 4 comma 0. This is the linear combination basically. Okay, if you see the results over here, so we got the result that we got is 34 minus 1. So if you see in here, so if you put 8 over here and if you put 1 over here, okay, so this will give you 2 minus 1 plus this is 32. So this is 32 and then this is 0. So now if you sort of add these things together, 2, this is 34 and this is minus 1. If you see, this is the first row over here. Okay, so what I did is I took this row multiplied by this entry, and then I took this row multiplied with this entry and added them together. So I got the first row. So in the second case, what I will do is, sorry, I got a call. In the second row, what I will do is I'll again take this row, multiply it with this entry, and take the second row, multiply with this entry, and add them together. Okay, if you want me to get the first row we got 34 minus 1. So we got 34 minus 1. So now in order to get the second row, what I told you, I'll again take the similar thing. I'll take this 2 comma minus 1 plus. Now I'll take the second row 4 comma 0, 4 comma 0. Then I'll multiply this by 2 and 1. So I'll multiply this with 2 and multiply this with 1. So this will be 4 comma minus 2 plus 4 and 0. So if you add this together, this will be 8 minus 2. So if you see it here in the answer, so this should be 8 minus 2 or something. What is it? Have we done some calculations wrong if you see it? So calculations will be here and there, but I don't care about that. So here it will be, so if you take, it should be the linear combinations of this. So you can check out the calculations though. So if we have a matrix A, we had a matrix B, the column way basically means we'll get a matrix C, and the columns of this matrix will be the linear combination of columns of B. Okay, so columns of this will be linear combinations of columns of B. You'll take one column and take the multipliers. You'll take the other column, take the multipliers over here. Okay, so the first, let's suppose this is column, this is row 1, this is row 2. Okay, so you will take row 1 plus row 2 and some linear combination to get the rows. Let's suppose this is A and B to get the rows of C. Is the column way clear?
Yes, sir.
Somebody is calling me and I had to leave the session, so I'll again join it. Okay, nice. So Rian, is it clear? Zubair?
No, sir. Can you explain again?
Nice. So what I'm telling you is, let's suppose we have a matrix. Let's take a matrix 1 2 4 1, and we have another matrix 3 1 2 6. This is our matrix A, this is our matrix B. So we have another matrix we'll get out of this is C. So what I'm telling about this C is that the rows of the C will be the linear combination of these rows of B. So how would you do take linear combination? So we'll take this row multiplied with something plus take this row multiplied with something. So what I'm telling you is that, so in order to get this row, basically, if you want to get this row, so you'll take this 3 2 first, 3 comma 2, and multiply it with this. Okay, then you will take the second row and this will be the multiplier. Let's call this as, let's suppose, row 1 and row 2. So you are taking linear combination of row 1 and row 2. That's how you get this row 1 of column C. So you'll take 3 2 and multiply it by 1 plus 4 multiplied by 3 comma 2. So you will get 3 2 plus 12 comma 8. So when you add these things together, it will be 15 and 2 8 16. So 15 16 will be the first row over here. If you write it, it will be 15 and 16. So accordingly, you will get the second row. You will take the first row and take this multiply with this element. You will take the second row, multiply with this element. Is it clear now? Nice. So the only conclusion I'll make here is that you have to basically sort of have the intuition about is that the columns in this C, the rows in this C basically are the linear combination of rows of this B. So we saw the first method. The first method was traditional method. So in which we took the rows and columns and multiply them together to get each entry. Then we had this column way, where we took the columns of this matrix and columns of and multiplied it with these factors. So take a linear combination. So the columns of C are the linear combination of columns of A. Now I did it the row way. In the row way, I told you that the columns of the rows of C are the linear combinations of rows of matrix B. Is it clear? Are the three methods clear so far? Nice. So now I have one more method, maybe two more methods. So let's call it the fourth way. 1 2 and 3 are fourth way. So fourth way, I'll call it a outer product way. Outer product way. Let's first define the outer product. So what does outer product means? Let's suppose we have a vector 1 2 3, and we have some other. This basically is vector v1. Let's suppose we have this v2 transpose. We'll transpose this vector. So it will be 4 1 2. So you know that this vector's dimensions are 3 cross 1, and this is 1 cross 3. So you will get a full-fledged matrix of 3 cross 3 from here. Because how you will multiply? You will multiply this with this. So 4. So you will get the first entry 4. Then maybe the second entry you will get by using the first and second you will get 1. Then you will get 2, and the second thing is you will get 8, 2 and 4, you will get 12, and then 3 and 6. So do you agree that by multiplying this v1 and v2 transpose, we'll get this matrix? So this is called as outer product. So if you have attended a numpy session, in that we described this outer product. Okay, so now I'll use this outer product to compute the matrix multiplication. Let's suppose I have this matrix 1 2 3 and 4, 1 0 4 1, something like that. Let's make it 2. This is my matrix A, this is my matrix B. Carefully see what I'll do is, so I'll take this one and I'll take this one. So basically I'll take a vector, a column vector of A, and I'll take a row of B. So you know that I'll do 1 2 and I'll perform an outer product with this 1 2, with this, plus I'll take this 3 4, I'll perform an outer product with this 0 1. So when I add these things together, I'll get the matrix C. So again, if I do it, so I'll get 1 2 2 4 out of this, plus from this what I'll do is I'll get 0 3, I'll get 0 4. So if I add these things together, so I'll get 1 5 2 and 8. Calculation can be here and there, but you understood the idea. So the idea here is take the column of matrix A and the row of matrix B. So in that you'll get a whole matrix, you'll get a new matrix like this. Okay, then you will take the second column, you'll take the second row. Okay, so you'll get again the whole matrix. So this way, by the summation of outer products, okay, I got this matrix C, I got the matrix multiplication. Okay, do you understand this way as well? Nice. So how many ways have we discussed so far? The first way was the traditional way, in which you'll take one row and the corresponding column, and you'll get one entry by entry you'll calculate. The second was we took the columns of basically A and we got the columns of C. Then we took the row picture. Then we saw the outer product way. I have, let's suppose we call it the fifth way, blockwise matrix multiplication. Blockwise matrix multiplication. So in this, let's suppose I have a matrix A, then I have a matrix B. If I want to multiply them, I can sort of, the beauty about this matrix multiplication is that you can do one thing, you can have blocks of this matrix. You can divide into blocks. Let's suppose we'll divide this, if it's a huge matrix, that's a million by million records. So you can have A1 block, A2 block, and A3 block, and A4 block. So let's suppose you have B1 block, you have B2 block, B1 and B3 and B4. Let's suppose you sort of divide this matrix into blocks. So now, if in order to get C, what you will do is, let's suppose this itself is a matrix now. Okay, so what you can do is you can again do the similar thing. You can take this A1 multiplied with a B1 to get this block. So again here we'll convert into 4 blocks, C1, C2, C3 and C4. In order to get the C1, so what we'll do is we'll multiply this A1 with this B1 plus this A2 into this A2 with this B3. This is how we'll get the C1. Accordingly we'll get the C2, C3, C4. So if you have a huge matrix, let's suppose, and you want to do this blockwise matrix multiplication, so you can convert this into blocks, and you can convert A and B into blocks and get the blocks of matrix matrix C. Is the block wise matrix multiplication clear? Why I showed you these many ways? Why? What is the reason behind that? The first reason is to tell you the intuition that there's not only one way to compute the matrix multiplication. And the second most important thing that I have, the first one is quite clear. I wanted to show you different ways in which I can multiply matrix. That's the first way. That's the first sort of motivation I had. The second motivation I had basically is, how many of you know about benchmarking? Because whenever you have to buy a device, you see benchmark scores. You see this GPU is performing this much, CPU is performing this much, phone is this much, because they show some scores. So how many of you know that benchmarking if you watch these tech videos? Okay, so in that, what they'll do is, for example, they have different bench, like cinnamon benchmark is there. There are a lot of benchmarks. If the new CPU comes, and they have to compare it, so what CPU is, how much is better than the older one, and how good does it perform? So they are making what's called as benchmark. So benchmarks, basically, there are some programs that run, and they'll give some score. So the higher score basically is better. Higher is better. So if you just see the comparison between two phones, let's suppose Android and iPhone. So now if you want to see how this performs, so they'll have benchmarks. Let's suppose one benchmark is cinnamon. It is a program. You'll run that onto your iPhone, and you'll run that similar program onto your Android phone, and you will see the scores. Whichever gets the higher score, basically we say that this performs better on this benchmark. Okay, so this is the brief concept of benchmarking. Okay, this is the whole concept. What I want to talk about benchmarking. So this matrix multiplication basically is used. This matrix multiplication is used for benchmarking mostly GPUs. If you see, if you can also benchmark CPUs. Okay, so I took a course known as computer high performance computer architecture, HPCA. So in which you have to make computers really faster. So you have to basically give a benchmark on that. So we had to make a benchmark ourselves. So we made what is called as checkered matrix multiplication. Okay. So if you know, there is something in CA called as, we have spatial locality and things like that, and people and computers exploit those things. But if you perform this checkered matrix there will be page misses, a lot of page misses. I don't want to get into the details, but just remember that this matrix multiplication, the variant of this matrix multiplication, is used in benchmarking. That's used in benchmarking of CPUs, GPUs. That's why you should know how to perform this matrix multiplication. So you'll find different ways of performing matrix multiplication, and you can create a benchmark yourself. So how many of you can now raise hands so that they can say that we learned many ways and we learned different and got the intuition of how the matrix multiplication is done? Now can you without the rote way doing the matrix multiplication, will you be able to do the matrix multiplication by having all of these things in your head? Maybe they will need maybe some revision at some point, but I hope that I at least conveyed this much to you, that there are different ways in which you can multiply matrices, and why is the matrix multiplication, it's done in certain way. Let's wait here for, let's suppose, 20 seconds to take some questions. Salim, so have you any question?
No, sir, not yet.
So have you understood the ways the matrix multiplication is done, and why is it being done in a certain way?
Yes, sir, surely.
Nice. Can I move ahead then?
Sure, sir.
Okay. So I'll write some properties as well for the completion purpose. I'll write properties of matrix multiplication. The first property, if I want to tell you, is that if I have a matrix A and I have a matrix B, then I have a matrix B and A. So what is the meaning of this basically is, if I applied this B first followed by A, will it be equal to if I applied A first and then B? So in our terminology, let's suppose if we applied rotation first then shear, so will it be equal to if we applied the shear first then rotation? Will it be equal? What do you think? Will it be equal? Amir is saying no. Okay, let's see that in the animation to sort of justify this first, that this basically is not equal. So let's justify that by the animation. Let's suppose we have this matrix M1 and M2, and we want to find if M2, if we can reverse the order and is it equal. So in our case, we have the rotation and the shear. And I think screen is visible. Is it visible now? Yes. So now let's suppose that we have this, we'll apply the shear first. Let's suppose we have the shear, and then we'll apply the rotation. So this is the rotation and that's the shear. So if we apply first shear and then rotation, this is what we got. So this is the transformation that we got. This is the basically the matrix multiplication that we got. So it landed at 0, 1 and 1, 1. We can capture that into matrix if you know. So we'll just keep that as columns of this matrix. So now we'll apply the rotation first and afterwards the shear. Now you can see we got a completely different matrix. Okay. So that means by seeing this animation, it is pretty clear that this is not equal. So this is a goddamn proof. So if somebody says you, is this a proof, you can just show the animation. That this is called as symbolic proof. There are different proof techniques. This is called as symbolic proof. If somebody for example wants you to show something and you show it in a pictures, or maybe you show it in some visual way, let's call it visual proof. Let's mostly people will say this these are visual proofs. Symbolic basically they can be represented like you just use symbols. So visual proofs basically are the proofs in which you show some animation, but it's really easy to sort of get convinced by these things, so that you must check these things. But here you it's easy to check sort of thing. So you will apply the B first, and then you will apply A, and you will see where the transformation landed. Then you will see apply A first and apply B first, and you will see where did this land. So you'll pretty clear see that these things are not equal. So we can see that matrix multiplication basically is not commutative. It is not commutative. You can also give a proof by using the mathematics by computing all these entries and then see these entries are not equal. Okay. Then what do you think? The problem associativity. If I sort of multiplied A and B first and then multiplied C, and if I multiplied B and C first then multiplied by A, so is the matrix multiplication associative? So what do you think? Is it associative? I am unable to see your reaction. So what do you think? Is it associative? Rian, what do you think? Is it associative?
I don't think so, sir.
It's really easy. Like Salim, what do you think? Is it associative?
No, sir. It seems not.
Okay, let me just show you a surprise, because both of these things say the same. As you know that we'll apply this C first, followed by this B, and followed by this A. It's not like that we'll because we have to read the rotations from here to here. And here it is also the similar thing. So even if you are multiplying C and B together, this basically means you're applying C first, B, then A. So here you have to see order of transformations. So how basically the space is rotated. So in this first case, what you will do is you'll apply C first, okay, and then you will apply B and A. So mathematically they might look different. Why do they look different? Because I put this base, I told you multiply these things, then this C. But when you are applying the rotations, that basically means that you have to apply rotations from left to right, right to left. Sorry, you have to apply rotations from here to here. So you'll apply C first, then B, and then A. So you have no concept of clubbing. You have no concept of clubbing things together when you apply these transformations. So if I show you a visual proof again, so if I show you a visual proof, let's suppose I'll show you a visual proof. Let's suppose I have this ABC. So what this basically says me that I'll apply this C followed by B. Then to the whole transformation I'll apply A. Okay, let's do this. So I'll apply this C, and then I'll apply now B, and then I'll apply A. This is what I got. Again, to rewind it back. So this is my plane in the initial original position. So I'll apply C first. So I applied C followed by B, then A. This is what I got. Okay. Now if I do this, AB by C, this basically is again the similar thing. You have to apply the transformation in the similar fashion. You have to apply C, then A, and then B and A. If you see this, you apply C, then B, then A. So this is what we'll get. So basically, if you see them visually, they are similar things, but mathematically they may look similar because we are clubbing different things. But when you apply the linear transformations, you know that we have to go from right to left, and here it does not matter. For example, if you sort of club this A, B, or B, C, clubbing basically works in in the symbols, and in the visual representation. You saw that the order matters there. What order you are applying these transformation into. So that we can see this property is associative. So this is sort of an exercise for you to prove it mathematically now. I showed you a visual proof. Now you have to take matrix. Let's suppose you take general matrix A, B, C, D, some other matrix x1, x2, x3, and you will prove this associative property. Okay? There are a lot of things that I can talk about matrix multiplication, but I think I can stop the discussion of matrix multiplication over here, and I'll move forward to the next step. Okay, there are different properties, but I wanted you to show these properties. If somebody asks you the visual proof, you can show the visual proofs, and you can also this associative property can also be shown visually. So I showed you a visual proof. Maybe you can prove it mathematically by using the equations of what we discussed in this matrix multiplication. Okay, now I'll go on to the determinants. Okay, if you have understood really well this linear transformation, if you understood this matrix multiplication concept really well, it'll be really easy for you to sort of grasp this determinants concept. It's not that difficult. It's really easy if you now have the basics, if you now sort of understand all of this stuff. And before going into the determinants, I'd also like to show you some visual representations in 3D. So far we have been seeing everything in 2D. Let's suppose if we have to see the things in 3D, how these transformations can be done. I want to show you that in 3D. Let me just find that. Okay, so if I have to show you the linear transformations in 3D, so how I'll do that. So transformation basically is it means you'll take an input vector, and out of that you will spit an output vector like this. This is basically the normal meaning of a transformation, linear transformation in 3D. So you'll take a 3D vector and you will spit out some other 3D vector in the same plane. And now this is a 3D plane. We have x-axis and we have y-axis and we have z-axis. So these are the three I hat, j hat, and k hat, we call them. The basis, basically basis of 3D. So this is a 3D plane made out of these grid lines. So the transformation will happen to all of this 3D if you see it. So this is the transformation, linear transformation. This is how it will look visually in 3D. Okay, so this is the 3D. Let's suppose this is a vector which we want to see what will happen to this vector. Let's suppose we have a vector. This is I hat, j hat, and k. This is what is the meaning of transformation. For example, this sort of got translated. What will happen to this vector? I hat went to 101, 10 minus 1, because you know that we have to just keep track of where the basis vector land. So here you can see this I hat, it landed at 0, 1 0 minus 1, and j landed at 1 minus 1 0, and k landed at 1 0 1. So if you need to, if you have any vector x y z, now by just clubbing these three things together in a matrix, and you can just have any random vector x y z and then multiply with this matrix, and you will get the linear combination of you'll get basically where that vector will land. Okay, so these are some transformations that can happen. So the only, again, the point here is these lines should be they should remain evenly spaced and parallel to each other, and the origin should remain fixed so that it is a linear combination. It's a different this is in 3D, so I cannot show the things in 4D because the first thing is that our brain is not able to visualize it. That's the power of algebra. So power of algebra is that you can sort of do every calculation that you did for 2D and 3D, and but here we have the visual power. Our brain is able to visualize these things. But now if we have 4D things, if we have vectors 1 2 3 4, this is a 4D vector, so we call it R4. So because every here number is a real number and it lives in R4 vector space. So we can also apply linear transformation onto this. Let's suppose this is some vector t, we can apply some linear transformation tv l of t over here. So it will spit out some other vector 1 2 4 6, let's suppose some other vector it will spit out. But you cannot visualize this now, but algebra gives you the power to compute this. So you might have heard about string theory, where they contain that universe has some 32 dimensions. This is the meaning of dimensions basically. So here everything, if you have to show a coordinate in the universe, you just maybe, for example, for this pen you can just take let's suppose this corner as origin, and then you can just measure x y and z axis. So 3D, we call these objects as 3D because they have length, breadth, and height, and it's easy to represent them in 3D because this is how our world works. So if you see string theory and if you see quantum mechanics and things like that, there we go into higher dimensional spaces. So tell you an interesting story. It is believed that maybe we live in 3D and we are able to see the 2D things as well, and maybe if there are some pure 1D things, we will be able to see them. And there is the hypothesis that the angels, they live in some 4-dimensional space. Angels and then devils, they might live in 4-dimensional space, while they can see the 3D picture and the 4D things as well. But our brains are not tuned in, and they cannot comprehend these things. They cannot comprehend the things in 4D. This is just the hypothesis. Surely we'll test it out in the afterlife. But here you may assume that there are worlds within the world which have different dimensions, and it's very difficult to comprehend into that. Okay, how can a world exist within a world? So there is something, a concept called as multiverse. So multiverse basically means there are different universes. So we are living in one universe. There may be some other dimension in which there is other universe, and their laws of physics and laws of nature will be different there. The thing here is we can visualize 2D and we can visualize 3D. So that we did, and we can also visualize 1D. But out greater than this 3D, like 4D, 5D, greater than this 3D, we cannot visualize. So I showed you the visual representation of this. Now the mathematics has the power to do all the calculation, all the computations that we did for this, where we could visually do this, where we could visually sort of explain all of these things. But in greater than 3 dimensions, we cannot see them. But mathematics has that power. We can do all the computations that we're able to do in 1D, 2D, and 3D. So do you see the power of mathematics? Mathematics, I told you in the first lecture, mathematics is basically a language. So it's a language that everybody should know how to speak. But mathematics is so beautiful. If you have to model anything, you can model it maybe 2-3 words. Can you imagine that E is equal to mc square? This equation was enough to create an atom bomb. Okay, so this is just a succinct representation of the nature. So if you tell me what mathematics is, I can give you a one-line definition of mathematics. Mathematics basically is a language of nature. So how nature speaks. So I had a discussion with Rian as well. So Rian thinks that there are a lot of constants in nature. I think there are 30 plus constants in nature which have some constant values. For example, this gravitation G, it has a constant value. So if it was here and there a bit, the universe would not exist. There is something called as Planck's constant. There's Boltzmann's constant. A lot of constants exist in nature. But how do we capture them? By using the mathematics. And for example, there is symmetry in mathematics as well. If you see gravitation, you have seen that law G is equal to G m1 m2 divided by r square. This is how we capture the gravitation. And then there is a same law in by symmetry applies that on the charges as well. So there is some constant, maybe some mu or something, q1 q2 divided by r square. So that's not how nature, maybe there are different properties, but if you see the laws underneath, they operate on the similar level. If you see the things, why are these planets circular? Okay, maybe they're a little bit ellipsoid. So if you see our earth, it's like an ellipsoid. But if you see other planets, they're also ellipsoid. Why is even the raindrop ellipsoid? Okay, why is the moon in the similar way? Okay, there is a lot of symmetry, and this symmetry we can capture it by using the mathematics. That's why there is a beauty in mathematics, and it needs eyes to see that beauty. So mathematics should not be introduced something which is really boring subject. So mathematics basically captures what is happening in a succinct format, so we can convey it to somebody else. There are different languages that do exist in the world, but mathematics I consider it as a language. So whenever I have an equation, I try to read it in English. So for example, I wrote that equation summation of something over here, I guess, here. So if you are able to read it in plain English, then you are seeing that you know the language, you know this language of mathematics, and you know how the world works. Okay, so do not consider mathematics as some jargon, and it's just for the people who write equations a b, some symbols. It's just a language of nature, how the nature works, and we have a succinct representation as well. Now let's go on to the determinants. Now if you see this is also linked to the linear transformation. That's why I told you upfront that this linear transformation, it's a really important topic to understand. So if you understood this linear transformation, whole of your algebra journey will become really easy. So what is this determinants now? So for example, I had that space like this. Okay, so somehow I transformed it in certain way. So I transformed it like this, let's suppose. If you see, I transformed it like this. Now you can see in the transformation, you see there is an increase or decrease in area. So there is increase or decrease in area. Let's suppose I had this vector. So this was my I hat and this was my j hat. So let's suppose after this is my I hat and this is my j hat, let's suppose. So as you see that it swept this much area. Initially we had this much of area. Now you see this area got increased. Okay, in some other transformation maybe area will decrease, and I need to capture this. I need to see if I apply some linear transformation, what will happen to this areas. So I'll call areas. So I'm speaking about 2D right now. So in 2D we'll have the area, in 3D we'll have the volume, in 4D we don't know what we'll have. Okay, so in 2D if I had these vectors, let's suppose this is our I cap and j cap. So these are the two vectors that we have. So this was the area basically under these two lines. So now when I apply the transformation after that, so I got a bigger area. So I want to quantify this. I want to get a number how big this area became. Okay, that is given by the determinants. So if you tell me what determinants give me, so they basically just give me how much the area was bigger. So if I have again a plane like this, okay, so this is my axis, let's suppose. If a transformation happened, so it just stretched these lines. So initially I had 1 0 as I cap, and in the j cap I had 0 1. So after transformation, what happened is I just stretched out this I cap to 2. So it became 2 0. Okay, after that, and J cap remained the same, let's suppose. So this is after transformation. So you know that initially the matrix was 1 0 0 1. So after transformation, our matrix became 2 0 0 1. Now you know that the area initially was 1. So if you know this is the area, so 1 and 1. So the area basically, this can be considered as a rectangular square. 1 multiplied 1, the area was 1. Okay, and afterwards, if you see, I just did a transformation, so I just this I cap got stretched. So now the area became 2, because you know that now this is the area. So the area became 2. This is the determinant. So I got that. I got from, if you know how to compute determinants, we'll multiply. For example, this 2 multiply 1 0 multiply, we'll get 2. This is how we got this 2. So this is why we multiplied in a certain way, and there's a really good proof of this, how our determinants computed. So if we have, let's suppose, some vectors a, b, and c, d. If after transformation, we applied some transformation, and these vectors went to x, y, w, z. Okay. So in order to see, now we can see that it stretched space, it warped space around, but I want to see how much stretch was there, or how much it shrink the space. I can just compute determinant in this way, xz minus yw. So this will basically quantify the transformation. Okay, this is in 2D. Everything happened so far in 2D. We can extend to 3D. Let me again show you the animation of the determinant so that you understand it really well. So I'll open that animation. That's why it's really important to teach algebra in this way. Otherwise, you'll feel like something else is happening. Okay, so I'm ready to show you that. So generally, what transformator, they stretch the space. For example, if this is the transformation, so it stretch the space, or it will squish the space. It will make the space smaller. So if you see it here. So let's suppose if we want to see by how much this stretch, or by how much exactly the squish happened, so that's given by the determinants. So let's suppose initially we had this much of area. If you see, this is the area initially. So after transformations, you saw that this area got scaled by some constant, by some scalar, that is c. So we call this c as determinant. Okay, that this is in 2D, and we can extend it to 3D as well. So let's suppose this is our 3 0 and 2 0. After this is our transformation. This is what will happen that I showed you. It will just scale this x by 3, and it will scale this by 2. So initially the area was 1, now the area became 6. Initially this was the area, this much was the area, and now after the transformation, this is what happened after transformation. Now the area became 6. Now if you see that the determinant of this matrix basically is 6, the new area becomes 6 if you just see this. Okay, and I can also show you it in 3D maybe. So is the 2D case clear so far? Is it clear? So what's the meaning of determinant? If somebody asks you what's the meaning of determinant, determinant basically captures what happened after linear transformation, how much there was a stretch, or how much there was a squish in that space. So when we apply the transformation, so in order to keep a track, what we'll do is, for example, we'll just keep the track of these squares, what happened to everything, and then we can show you. Let's suppose I'll again show you something. So let's suppose this is my area, and I want to see how much this area got stretched. So I can just fit in many of these different small squares. So if I apply a transformation now, so after what will happen is, it will either stretch or it will either squish. So you saw that this area got changed. If you know the integrals, you see how we compute the areas. This is how we'll compute this stretch of the area, and we'll get that constant out of that, and we'll see this basically is done. And this is, let's suppose, 6a. Initially we had the area a, now we had the 6a. 6 basically is the determinant of this transformation. Transformations basically are matrices, they're captured in matrices. I hope that this concept is clear. So again, if I can find animation in 3D, maybe I'll also like to show you it in 3D. In 3D, what will be the meaning of area? It will be volume. Okay. Let's suppose if I could find it. Yes, I think I can find it. So let's suppose this is a 3D cube that is represented by I cap, j cap, and k cap, unit cube. So now if I applied some transformation, something will happen to this cube. Okay. So it got stretched, and this basically is called parallelepiped. So if you stretch a cuboid in some shear manner, so whatever you get is called as parallelepiped. So there is an area associated with this, and you get that out of the determinant. Is it clear what determinants are for? So determinants basically they compute the basically they quantify this stretching or squishing, But there is a twist. There is a twist is that determinants can be negative. So what is the meaning of negative basically is, so if we have this I cap and j cap, so if we have this I cap and j cap and it's stretched in somehow, but the orientation of the space remains same. So the orientation remains same, then we call it a positive determinant if the orientation remains same. Orientation remains same. But what happened if this orientation was flipped? So if this orientation was flipped, I cap went into some negative and y cap went into some other negative value, so we'll get a negative determinant. This negative and positive have to just deal with the orientation. So how basically the squishing was done. If it was done in the similar direction, if we had this I cap and j cap, and after the transformation, they still had that direction. If they had the negative direction, then we'll get the negative determinant. So everything, this positive determinant and negative determinant have to do with the orientation of space. So orientation after transformation. So if the orientation was similar to what it initially had, then we'll have positive determinant. If the orientation was sort of flipped, then we'll have the negative determinant. That is the whole concept of determinants, and you know how to compute the determinant. If I have, let's suppose, a bigger matrix A, B, C, D, E, F, G, H, I. So how I'll compute with this? I'll just multiply A and then compute the determinant of this portion. E, F, H, I. Again multiply these things, and then I'll take plus. I'll take this B, cancel this column and cancel this row, df gh, df gi, and so on. So this is how we compute the determinants. So maybe for in the assignments we'll give you examples to compute all of this stuff, but here I want you to remember, and I want you to know the geometrical interpretation, and the mathematical part you will do it on your own. Is the concept of determinants clear? Yeah, let me ask you a question. If for example I had a transform, if determinant is equal to 0, so what will the meaning of that determinant is 0? What is the meaning of determinant is equal to 0?
The area reduces to 0.
Yes, the area will reduce to 0. What will that mean geometrically? That will mean two things. The first thing is, if we had, for example, this plane, and in the plane, as you know that, for example, if we have this I cap and j cap, so they'll basically span over the whole space. So determinant will be 0 if they span the line now. If they only span the line. Okay, span the line basically means they become linearly dependent. I hope that you remember the concept of linear dependence and dependence. Otherwise, they become 0. So in both the cases, determinant can become 0. For example, if I have this 1, 2, and 3, 4, you know that these two vectors are linearly independent, because you cannot get one vector from the combination of other vectors. Okay, so you know that these things will span, this will span whole 2D. Okay, this will basically span whole the 2D, whole the 2D plane. So if I applied some transformation onto this, you know that this will land somewhere and this will land somewhere. Let's suppose these things landed at 4, 6, and 8, 12. The transformation happened in such a way, initially let's suppose these vectors were like this. So I'll just make a rough sketch, and these vectors for example were like this. But when you sort of transformed it, what will happen to the space, and these vectors, they landed at the same line. 4, 6 basically let's suppose means 4 and 6 means this vector, and this 8 means the scaled version of this vector. So they basically land on the same line, these vectors. So in this case, the area initially was, for example, this much. The area was, for example, this much. Now you see this area became 0. And in the other case, if they landed at 0, 0, both of them land at 0 0, or maybe one of them land at 0, so the area will become 0. That is the meaning of determinant becoming 0. Determinant can become 0 in two ways. The first is that the vectors that we see, that they'll initially, if they were spanning, for example, whole 2D, we're speaking this in 2D. So if we had these two vectors who are spanning whole the 2D space, so after transformation what happened, they'll now span just a line. Okay, it somehow got squished down to a line. Otherwise, one more thing can happen is that these vectors can just go boil down to the 0 vector. One of them can boil to down 0 vector, or both of them can boil down to 0 vector, so that they'll get the determinant 0. So spanning a line basically means spanning line basically means it will become linearly dependent. Is this clear? What is the meaning of determinant being equal to 0? It will be really important. Why? Why will be it important? Because when we will do the inverse and stuff like that, because in inverses computation you must see determinant. If the determinant is equal to 0 for some matrices, they are called as singular matrices. Singular matrices. And they are also non-invertible. I'll say what this invertible word means. Just pause here for a second. But just remember this: determinant 0 means that two things can happen. One thing, like we're only speaking in 2D, and it also extends to 3D and high dimensional spaces. In 2D, what it means is the columns of that matrix will become linearly dependent. So they'll become linearly dependent. Basically, in 2D, the span was whole 2D. Now the span will be a line. So in 3D, so what will happen? In 3D, it can be like they'll span a plane now. Initially, they were spanning the whole 3D. Either now they can span a plane, or they can span a line, or they can just be spanning of the origin 0 0 vectors. So in 2D, it can be spanning a line or a dot. So that's why meaning of the 0 is. So 0, one of them can become 0, or both of them can become 0. So that's the meaning of determinant being 0. So the matrices which have the determinant of 0, we call them as singular matrices, or we call them as non-invertible, and we'll see why they are called non-invertible. I was thinking not into determinants first, but I wanted to tell you what inverses are. For that, I need to get the geometric intuition. So that gave me that idea that I should introduce the determinants first. Just for your convenience, again to reiterate, determinants, they quantify the transformations, what happened because of the transformation, how much the stretch was, or how much the squish was within the space. And the second thing is, we can compute the inverse of only those matrices for whose determinant is 0, and we'll get to know the intuition why are these matrices non-invertible and things like that. Is the determinants clear? Can I move ahead? Nice. I'm just explaining everything in 2D, but if you have questions regarding 3D, 4D, and maybe for 3D I can visualize you, and for example 4D, if in 4D, if these vectors went to, let's suppose, some 3D space, and now they span some 3D, or they span some 2D, or they span some 1D, that's again basically it is decreasing the volume. Here it was decreasing volume, let's call this hyper volume. So in 4D it is decreasing this hyper volume to 0. Okay, it will extend accordingly. But again, rewatch these lectures so as to get these things ingrained into a head. You know what is happening basically, and you get the intuition in 2D and 3D, and then you can extend it to higher dimensions. I hope that the computation of determinant is clear. Now I'll move to an important topic of inverse of matrices. Inverses. So I'll call it matrix inversion, or matrix inverse of matrices. Now you know that a matrix basically defines nothing but a linear transformation. So if I have a matrix like this, so if I have a matrix, let's suppose I have a matrix 1 2 4 5, you know that this is nothing but where the I had landed, where the j had landed. This is in 2D. So in 3D, if I had 3 columns, 1 2 4 6 8 9 2 1 0. So this basically means where the I had landed, j hat and k hat, where are these basis vectors landed. So this is the meaning of the matrices basically. So what I want now is, for example, if I applied this transformation onto a space, can I undo this transformation? So I applied a transformation. Let's suppose I applied transformation T onto some vector space. Let's call that V. Okay, I got some TV. Let's suppose V transformed, or V dash I got out of this. So now I want to take this V dash and I want to apply some transformation T inverse so that I get the V back. In the matrix terminology, let's suppose I have this matrix A. This matrix has an effect. Okay, it has an effect. It does something to the space. It basically does some transformation. So I want to apply A inverse so that it gets neutralized. So if I want to show a transform which does nothing, that transformation is called identity transformation. So if I'll write in 2D, so 1 0 0 1, it's called the identity matrix. Why? Because it does nothing. So if you multiply x y, so you'll get back x y. So x multiplied by this will be x0 plus y multiplied by this will be 0y. So if you add them back, you'll get xy. This is called as identity matrix. Identity matrix. So I had this A. Okay, A was some linear transformation. I applied this onto the space. Now what I want to do is I want to take this A and I want to apply the reverse transformation of this. So what will happen is that, so I'll get the identity. I'll basically undo the effect. So inverse is what they do is they'll undo the transformation effect. Whatever happened before by the transformation, if I apply the inverse of the transformation, it should undo the effect. So that's why I wrote A multiplied by A inverse should be equal to identity. Identity basically means leave the space as it was. Is the introduction about this inverses clear? Then I can show you the animations what I mean by the inverses.
Sir, could you repeat a little bit?
So what I'm saying is, let's suppose I have a transformation T. So you know that transformations basically are captured in matrices. So in 2D transformation can be captured as 2 1 3 1 like this. So let's suppose this is the transformation. So if I applied this onto some vector, let's suppose xy. So you know that now I've had transformed of x and transformed of y. So I'll have this vector will get transformed somewhere, this x and y. Now if I want to undo this, okay, I want to get some T inverse which will undo the effect. So if I apply this T inverse onto this, I'll get this xy back. That's what I'm telling. In the matrix form, if I have a matrix A which I applied to the vector space and which I applied to that 2D plane in 2D or 3D plane in the 3D scenario, so what happened? It did some transformation. If I want to undo the transformation, I'll have a matrix A inverse of this matrix that will undo the transform what A did. So if I got I out of this, so I'll call this A inverse as inverse of matrix A. Is this clear now? Because basically what I'm doing is I'm just undoing the effect that was done previously. Okay, I want to show you the animation, maybe if I have that. We'll take this inverse in larger detail because we have to also show you how to compute these inverse and stuff. But here I want to just show you the animation if I had something. Let's suppose I'll just make it. I cannot find the animation right now. Let's suppose I had this plane like this. So what I did is, you know that if I apply that 90-degree counterclockwise counterclockwise rotation. So in that, what I did is I had this and I rotated counterclockwise 90-degree. Okay. So if you remember that, so here we have written that matrix is somewhere. That matrix we have written somewhere. That matrix that was the counterclockwise rotation. This is the rotation. 0 1 minus 1 0. So 0 1 minus 1 0. So 0 1 minus 1 0. So this is the rotation that we had. Okay, so this was our rotation. So what it did is it rotated the whole space over here. Okay, it rotated in some fashion. Let's write that like this. It rotated 90-degree counterclockwise. Now if I apply something so that I get this rotation back like this, I'll go back to here. Basically I'll get nothing and I'll get identity back. I'll get the space in the original form. So here I'll have to have some matrix so that I get this 1 0 and 0 1. Okay, so how I can do this? If I want to do that, let's suppose I'll put 1 0 over here because I want to get 1 0. So 0, and now I want to get, so I'll put minus 1 0 and minus 1. So if I put this matrix, this will be R inverse. Just compute this multiplied by this, you'll get the identity. So this is the rotation counter 90-degree counterclockwise rotation. So this basically will be 90-degree clockwise rotation. Okay, so this is the matrix. So if you just take this, multiply with the column of the column 0 multiplied by this is 0, and then 1 multiplied by this will get this. One first column, the first column will be this. That's why I put the 0 here and 1 here. because I know I have to multiply this by 1. And then in order to get the second column, so I have to get 0 1, so I'll just multiply this with -1, and this will be 0. So this basically, this is the inverse of this. Okay, I just computed by eyeballing the things because I know how, what's the meaning of the inversion, what's the meaning of transformations. I just wanted to show you, if you have this R and it did something to the space, and if I want to undo the effect, I have to apply R inverse. So let's see again an example, because now the rotation is 0 1 -1 and 0. You know that this will rotate the any vector with counterclockwise. Let's suppose we have this vector xy. We'll see what will happen to this xy now. So what will happen to this xy is, so x multiplied by 0 1, and then plus y multiplied by -1 0. Then if you write it here, so it will be 0x plus minus y 0. So we'll get minus yx. So this is what happened because of the rotation. This is what happened to the vector after 90-degree counterclockwise rotation. I told you that this is the 90-degree now 90-degree clockwise rotation. So what is the what is that matrix? That is 0 1 0 -1 and 1 0, 0 -1 and 1 0. So if I take this vector, the basically the rotated vector minus y comma x, if I again apply this rotation, that is clockwise 90-degree, so I should get xy back. Let's see if I can I get xy back. So minus y 0 -1 plus, take this, multiply with this whole, x 1 0. So this will be 0 y plus x 0. So you got xy back. So I had R, I applied R inverse. So I basically, whatever the x here was, I got this x back. So from this, what I can do is, I know that if I again apply, if I sort of apply, if I can write just this as identity, I can write R inverse of R is equal to identity. So I had vector x, I applied the R first, then R inverse. So if I want to get this x back, so this thing should be equal to this I, identity. Basically, if I have vector xy 1 0 0 1, this is the identity, it will do nothing to this vector. So this x will get multiplied with this y will get multiplied with this. So you'll again get back xy. That's why I wrote that this R and R inverse should be equal to I over here. Is the concept of inverses clear so far? We have talked a lot about inverses, but I'll stop the today's session here because otherwise it will again stretch to more than half an hour on the discussion of inverses. So I'll just stop the recording and I'll take your questions.